All right, so next up, we're going to be talking about remotely positioned MetaSurface drone attacks. And this presentation is going to be given by, you good here? Oh, perfect. Okay, great. Okay, this presentation is going to be given by Jambil, who is a senior PhD student at Rice University working under Edward Knightley. His research broadly focuses on next-generation sub-terahertz wireless communication, security, and sensing. Recently, Jambil has been working on metasurfaces and wireless security, exposing devastating wireless attacks from adversarial metasurfaces. So I'll let you have the floor.
Can you hear me well?
Yeah.
Cool. Okay. Let's put it here. Hello, everyone. I'm Jambil, a PhD student at Rice University. It's my pleasure to be here and share our work on remotely positioned MetaSurface drone attack, RMD attack shortly. So this is a joint effort, and I would like to acknowledge my collaborators from Brown, Northeastern, and Rice Universities first. Well, as the title suggests, MetaSurface are an integral part of this work. To describe what they are in a high level, okay, let me go. To describe what they are in the high level, MetaSurface are these artificial engineering structures that enable controllable manipulation over the impinging wave. For example, they can enable absorption, focusing, refraction, and many, many other EM wave manipulation functionalities. Fundamentally, a metasurface consists of many sub-wavelength scale meta-atoms. Such meta-atom is shown in the form of a C-shape over here. Importantly, one can control the phase and amplitude response of the meta-atom based on its geometrical positioning and parameters. Then, intelligently arranging a group of meta-atom in a periodic fashion, a metasurface is formed, which enables these targeted wavefront manipulation over the impinging wave. Now, in wireless communication, metasurface has been shown to enhance communication performance in numerous ways. For example, a transparent metasurface embedded in a window, shown in the left figure here, has been shown to accurately redirect millimeter wave signals from outdoor to a location indoor. Similarly, metasurface on the right has been shown to mitigate polarization mismatch as the wave impinges on that surface and passes through it. And there are many, many other performance enhancement functionalities that are based on these metasurface designs. Now, in this work, however, we demonstrate that strong adversary could also exploit this metasurface jointly with the wavefront manipulation capability as well as the mobility in order to pose a serious threat in wireless links. In particular, we define and demonstrate the RMD attack and expose the security vulnerabilities of wireless backhaul links to such attacks. Now, to provide some context, wireless backhaul links are integral part of wireless communication, and they are widely employed for many critical functions, such as the financial trading in Wall Street. Such wireless backhaul antennas are usually positioned in a hard-to-reach elevated regions, such as rooftops or towers. And they commonly exploit these highly directive millimeter wave sub-terahertz links with large bandwidth. Now, because of these hard-to-reach area, as well as the narrowly targeted beams, one presumably thinks that these links are immune from the eavesdropping. However, we show that with the RMD attacker, who we refer as Eve can remotely overcome the physical challenges that I mentioned previously by exploiting the aerial mobility. Also, Eve can secretly manipulate the transmission wavefront by designing on-drone metasurface. And Eve can strategically improve your eavesdropping SNR by adjusting to a flight pattern. So the threat model of this work is as follows. So we're considering legitimate transmitter Alice and the legitimate receiver Bob that are communicating over the directional line of sight millimeter wave sub-terahertz link. So they're at center frequency of sub C and have some bandwidth B. Meanwhile, eavesdropper Eve has a knowledge of the center frequency, bandwidth, and the location of the communication parties. And Eve designs and employs her own drone MetaSurface in order to eavesdrop on this link. At the same time, Eve wants to be hidden and wants to attack the link, not exposing the attack itself. Coming to the strategy of the attacker, Eve's high-level strategy here is to manipulate the wavefront such that she can induce constructively interfering radiation pattern that is directed toward herself. In particular, she generates this anomalous diffraction. And to do so, she exploits the generalized Snell's law. This can be expressed with the equation over here, where psi and xi indicates the eavesdropping angle in the elevation and the azimuth and the elevation. And C is the center F sub C is the center frequency that Eve is targeting. C is the speed of light. Gamma is the impinging angle of the Alice transmission on the metasurface. And N psi and xi are the refractive index characterizing the environment. Now, the key parameter I want you to focus is this delta phi and delta y and delta phi delta x. Those are phase changes at the surface interface. Those are the key parameters. Now, without these parameters, meaning that when they are equal to 0, you can quickly notice that the equations reduces to standard Snell's law, which describes the change of the, in the direction of wave as it comes from one medium to another. However, in this attack, eavesdropper Eve purposefully manipulates these phase gradients such that she can induce phase changes at the surface interface such that she can induce d phi d over dy in order to induce a phase change in the y-axis and establish an eavesdropping link in the in-plane. Also, she purposefully induces phase changes in the x-axis in order to control the elevation of the diffraction angle. Now, not only that, but attacker exploits the mobility of the drone in order to dynamically control these phase changes and control the eavesdropping diffraction angle. Specifically, she takes the advantage of the roll, pitch, and yaw movements of the drone in order to orient the metasurface such that she can have her targeted diffraction phase gradients, which is here, the orientation of the phase gradient is designated with the rho, and the magnitude with the delta phi here. For example, she can control the roll movement in order to enable diffraction for different elevations. For instance, eavesdropper can be on the ground, and the communication can be occurred on the wireless backhaul link. So Eve can purposefully control the roll movement in order to eavesdrop from the ground. Yet, in the attack, Eve, by exploiting the drone, Eve also inherits these fundamental challenges of the drone system, such as the positioning inaccuracies. What it boils down to is that this, in turn, the positioning inaccuracies distorts the diffraction beam that is generated by Eve, and therefore her SNR will be degraded. Now, she addresses these challenges by adapting her flight pattern. And in doing so, what she does is that she contributes the fundamental knowledge about the metasurface, meaning the phase gradients, the direction of the phase gradients, as well as the magnitude. And she also takes into account the feedback from the remote eavesdropper SNR in order to adjust her flight pattern. And this allows Eve to essentially eavesdrop with a higher SNR. Now, if you notice, such mobility in essence allows Eve to mimic programmable metasurface. And in this work, we are showing that capability for the first time in this work. Now, next, the next step is for Eve to physically realize such metasurface. And what Eve does is that she designs this powerfully lightweight diffractive metasurface that are targeted for her platform, drone platform, which has very limited battery resources, as well as the small payload lifting capabilities. And we demonstrate the attack with the C-shaped splittering resonator meta-atoms here. Now, in order to establish a diffraction, what Eve does is that she intelligently constructs a group of meta-atoms, C-shaped meta-atom, such that she has a 2-pi phase shift over some spatial period gamma, meaning that linear phase change, while maintaining the linear amplitude response. By doing so, Eve can establish an eavesdropping link. Now, in order to next step here is to physically fabricate such structures. And the conventional way of fabricating the metasurface is this expensive, time-consuming photolithography method. However, in this work, what Eve does is that she quickly fabricates this metasurface in a couple minutes at the cost of a couple cents. And the way she does it is that she leverages this hot stamping technique, which essentially she prints these structures using the conventional office printer. And then she puts a metallic foil on top of that printer and passes them through the laminator. And what happens is that as the laminator heats up the metallic foil, the metallic dust from the foil will get transferred to the ink, and the metasurface will get metallized. And by doing so, Eve can essentially establish an attack very inexpensively and very fast. Another point I want to highlight here is that the choice of a substrate, in this case, paper. So this is not random either. In the attack, Eve not only wants to establish an eavesdropping link, but at the same time to maintain the original link between legitimate transmitter and receiver. Now, to do so, what Eve does is that she exploits these terahertz, sub-terahertz transmissive substrates, such as the paper, in the metasurface design. This allows Eve to pass through most of the energy between Alice and Bob, while also establishing an eavesdropping link. Now, next we implement the attack and demonstrate the proof of concept in the room scale scenario. Here, Alice and Bob are approximately 3 meters away, and the eavesdropper's RMD is in between. So this particular metasurface was designed such that it works at the 130 gigahertz, and eavesdropper is positioned in 20 degrees away from Bob, such that she's tapping onto diffraction peaks. Now, the testbed is as follows. This is a testbed which comes from the Keysight and the VDI. And here, the Alice is equipped with 40 dBi gain lens horn antennas, and Bob and Eve with the 20 dBi gain antennas. Another point I want to highlight here is that the C-shaped metasurface that I was describing, those are cross-polarized metasurface, meaning that it's strongly modulated in the cross-polarization regime. Therefore, eavesdropper's antenna is rotated here 90 degrees to tap on these orthogonal or cross-polarized regimes. Now, the first question here we ask is attack feasibility. Can Eve actually generate these eavesdropping diffraction beams and remotely intercept it? To answer that question, we perform this experiment. And as a baseline, we can see the scenario where Eve doesn't employ the metasurface drone. On the x-axis, you can see the frequency. On the y-axis, it's power at Eve. So clearly, without a metasurface drone, Eve essentially observes a noise here. However, when she does employ the metasurface drone, you can see she can obtain about 20 dB signal above the noise floor across these 5 gigahertz of bandwidth. What's happening is that this metasurface drone essentially allows her to induce these targeted phase changes at the surface interface and generate these diffraction beams and steer it towards Eve. Now, the next question is, okay, Eve is successful. Now, can Bob detect that the attack is occurring? Because if the link between Alice and Bob is disrupted, then clearly that will have a alert Bob, meaning that, hey, there is an attack happening. And the question here is, can Bob detect the attack? So here, on the x-axis, I'm showing frequency. There is, on the y-axis, power at Eve, power at Bob. This figure corresponds to the scenario when there is no attack occurring, meaning line of sight between Alice and Bob. And this figure on the right is the scenario when the Eve employs her MetaSurface drone. And looking at these two figures, you notice that they are very similar. In fact, there is only a few dB power shift on the right scenario. And the reason it is very similar and only a few dB shift is that the transparent substrate that I was talking about previously. The paper substrate essentially allows most of the energy to pass through and received by Bob. Now, what about those few dB phase shifts? Can Bob detect it? Well, it will be hard to detect for Bob because the similar variation will occur because of the swaying of the buildings. So we are considering backhaul scenario. Antennas are on the rooftop, and most likely they will be swaying, and there will be some misalignment. And this misalignment will actually cause similar effects. Also, the prior work has shown that the effect of the weather, the rain, the snowflakes, these frequencies, they're affected by those rains and snowflakes, and they can cause up to 10 dB power attenuation. And considering all these facts, it will be very, very challenging for Bob to detect whether the attack occurred in the first place. So which means it's a really devastating attack and challenging to detect. So this is ongoing work. We have been conducting large-scale experiments in Boston here, in the roof and the atrium scale, as well as the rooftop here. And the results so far look, they essentially implicate that the attack indeed can, we demonstrated the attack in the rooftop scale scenario as well. And here we're also characterizing the attack, different parts of the attack. So all of these things are current ongoing work. With that, I conclude my talk, and thank you for your attention. If you have any question, I'll be happy to take.
Hi, this is Ish Jain from UC San Diego.
Okay.
Very interesting talk. My question is about the motivation mainly. So we think in sub-6, we have an omnidirectional antenna, and whatever transmission goes, Eve can be anywhere and it will listen to the signal and it can get data, right? In millimeter wave, it is challenging, and thanks to your smart surface, and we can get some energy. But the end-to-end data is typically encrypted, right? So just by looking at the energy, like what information can Eve get out of this transmission? Like, have you shown any demonstration of, like, other than energy, if there is any other vulnerable information that can be broken?
Good question, very excellent question. So essentially in this work, we showed that in order to, in these highly directional links, usually it's hard to intercept the link. So what we showed is that Eve can intercept the link and without exposing herself. Now, the next question, what you can do with that data? That's another question. And well, prior work has shown that, well, we know that quantum computing is developing very fast. So the links can also be vulnerable to quantum attacks. That's one. The another thing, even if the links are secure, encrypted, and not broken, we have to acknowledge that not all parts of the packets are encrypted. So there are headers, there are channel state information that are not encrypted. So what it means is that Eve can exploit those information in order to establish side channel attacks. So in that work, in that context, that even if the link is encrypted, it's not secure, and a smart attacker as this can exploit these side channel informations.
Thank you.
Oh, sure. Okay, yeah.
Can I ask my question?
Sure.
Yeah, thank you. Thank you for this interesting talk and presentation. So I have a question here. Your MetaSurface is designed for a given frequency.
Right.
So in order to overcome this kind of attack, do you think that if we can, if a link can use a frequency hopping technology, so we are hopping between 3-4 different technologies, is still your attack, let's say, feasible, doable over that kind of the channels, or we have to design other maybe MetaSurface that can deal with range of frequencies? So thank you.
Very good question. So the question was about the different frequencies. As I mentioned, the particular MetaSurface was designed at 130 gigahertz, but it has a very broad response, so around 100 or 50 gigahertz. So it has a very broad response, it's one. But if you consider completely very different frequencies, then what Eve can do, she can have a concatenated metasurface. So one metasurface functions at a particular frequency, the another metasurface functions at a different frequency. So she can have these concatenated different metasurface and try to eavesdrop at different frequencies. So that's the thing that comes to mind at this moment.
Yeah, thank you.